Everybody. I'm going to be talking about equilibrium again. This is part 2. So I'm going to set the PowerPoint up so we can get going now. And I will share the screen with you. So I'll stop my video here and go to the PowerPoint. Okay, basically I'm going to talk about chemical equilibrium. In the last lecture I gave you, I was kind of introducing the subject, and now I'm going to get more into detail about the stuff using essentially the stuff that's in your book. I encourage you also to treat it and work on problems within the chapter. This again will be a little dry because I don't have any students interacting with me, but I hope you get what you can out of it. And then in combination with Dr. Gerhardt's or Dr. Powell's full lectures, you'll learn as much as you can when we're covering these chapters. It is directly related to next week's lab, and I hope that you will pay attention particularly to the math involved in solving these kind of equations. So let me go forward through this now and talk about each part. Equilibrium is a state in which there are no observable changes as time goes by. And basically what this could mean is, the key thing is no observable changes. So for example, if you have ice, water, okay, and it's at 0 degrees Celsius, ice is freezing, ice is melting, and water is freezing at the same time. And so you have ice cubes remaining in the system. Okay, so ice is melting and water is freezing, and that's at 0 degrees Celsius. That's by definition when ice is melting. There are two phases and they're at equilibrium as long as the temperature stays at 0 degrees Celsius. So that is an equilibrium state. Okay. Chemical equilibrium is when you have the rates of the forward and reverse reactions are equal. So for example, if you have a calcium carbonate and it goes this way to form calcium oxide plus CO2, under certain conditions, it'll go back that way as well. And say, for example, if you have a CO2 atmosphere with high CO2, the calcium oxide will go to the calcium carbonate, and also the calcium carbonate will decompose. So it'll go back and forth, and that's what the double arrow means, basically. And when it's going back and forth at the same rate, you have what is called the equilibrium state. Quite important to understand. The concentrations of the reactants and the products remain constant, okay? Because they're constantly going back and forth across the curve. I talked about the curve in the last lecture. If you got a reaction that looks like this, and it's mildly exothermic, and you got a hump like that, and then another one there, these are the reactants, A plus B, down here is C plus D, and in the middle, you have an intermediate form, A, B, C, D, and basically it'll go over here and it'll go back that way. And basically you will have all of the materials at certain concentration. At some concentration, you'll have the intermediate form here, you'll have the A and B, and you'll have the C and D there, because it'll go back and forth across that whole curve. Physical equilibrium is essentially when you have ice melting or water evaporating. So basically, if you have a bowl of water, the water is evaporating, as is the gas. Now at 100% humidity, what do you think is going to happen with 100% humidity? You put a bowl of water out. Well, at 100% humidity, nothing will happen. It'll stay there as a bowl of water. Chemical equilibrium, here's an example here of dinitrogen tetroxide reacting, breaking up to form 2NO2, and then I'll go back the other way, and so you have both of them together there. So for example, if we look at this reaction here with the dinitrogen tetroxide, and then it goes to form TNO2, you start with the NO2, and this is the starting point here. You're starting with NO2 here, and N2O4 has 0. This is 0, and this is some number, like just say 10. And then after a certain amount of time, this remains constant, and this remains constant after a certain amount of time. So you get, because you have the reaction going in both directions. That is called the equilibrium state. And if you start with N2O4, it'll go the other way. So essentially you'll get this constant and this constant if you go the other way. Now that's what you did for the lab in preparation for the lab we're doing next week, was essentially you took acetic acid and ethanol and mixed them together with some acid, and then you put ethyl acetate and acetic and acid in the other one. And basically the point was to get the equilibrium over the 2 to 3 week period, and you're going to be measuring that next week. Okay, if you start with both of them, here a certain amount, you'll end up getting a constant state eventually as well. You have an equilibrium between both. So here's an example of this kind of thing. Now, how did they get the numbers? Well, they got it by experimental reasons. They basically measured them at the different concentrations. And so you start with initial concentration amount of that just by adding them to a vessel, and then see what happens at equilibrium where they're going back and forth. And then you have the ratio of the concentrations between them. And if you notice, this is a constant here. So you have a constant, essentially, material. So it's essentially a constant. It's not perfect, but it's enough for the model to understand what's going on. Okay, now you look at, again, at the equation. This is called the equilibrium constant, where you have, this is the 2, and this is the products divided by the reactants. And in the case of gases, the concentration of the gas, the concentration of NO2 here would be equal to the partial pressure of NO2. So essentially you have a pressure aspect to this here. Now, if you, the K related to this is 4.63 times 10 to the minus 3. Where'd they get that value? Well, they got it from the previous slide. And this is the slide there. And you notice down here, the 4.63 times 10 to the minus 3 there, plugging all those values into that, they get that number. Okay. Now, if you got any general reaction, the constant will be equal to that. And again, this is the products divided by the reactants. And that's called the law of mass action. But basically, the mass is conserved across both of the sides of the reaction, and you essentially get a system where essentially it moves back and forth across, but the mass stays the same. So this is called the law of mass action. And the action is just because it's going from reactants, products, reactants, products, reactants, et cetera, and basically goes back and forth. So if you set it up like this, that's the K. And if K is much greater than 1, in other words, you have a lot of products and few reactants, okay, the equilibrium will lie to the right. So if you have more products than reactants, the equilibrium lies to the right. It'll favor the products. If the reactants K is much greater than 1, you have products associated with that. If it's much less than 1, it'll lie to the left, and that will favor reactants. And this is an example there. Homogeneous equilibrium applies to reactions in which all the reacting species are in the same phase. And in this case, they're both gases. Okay. And so basically you have those things too. This is set up that way. And again, you have the partial pressure of each of these. These are the pressure associated with it. Pressure again. In most cases, Kc is not equal to Kp just because of the nature of the different pressures associated with that. It's just a different constant because the units are not the same. The change in the number of moles of delta N there, Kp equals Kc times this, and that's the change in the number of moles here. And in this case, this goes from 2 to 1. This is 2 moles. This is 1 mole. So that will play a role in how that interacts. Homogeneous equilibrium is kind of what you're doing next week. And acetic acid and water mixed with those two. You have water associated with that, and then the constant. And basically, you generally do not include the units with it, usually because they cancel out under normal circumstances. Now, let's look at a problem here. The equilibrium concentrations of the reaction between carbon monoxide and molecular chlorine to form vinyl chloride. And first thing you do is set up the formula. CO plus Cl2 goes to form carbonyl chloride, like that. This is a gas. This is a gas, and that's a gas. Okay. Calculate the equilibrium constants, and notice they give you the concentrations of each one. Well, you set up the formula first, put the numbers in there, and then essentially you get the 220. What does that mean regarding the thing, the number of 220 there? Well, that number of 220 means it's all on the right-hand side. Okay, so essentially you have clearly a reaction that is favored to go to the right, but you'll always have some material on the left of things. The key is removing it from the right if you want, and we'll talk about that later. Okay, the Kp there, the difference is -1 associated with that. You plug the values in at this temperature, and you get the Kp is 7.7, but again, that's still to the right. It's just because the units are different there between the two. So basically the units are different That's why the numbers are different. Hopefully you all understand that. Now the equilibrium constant Kp for the reaction 2NO2 goes to 2NO plus O2 is 158 at 1,000 degrees Celsius. What is the equilibrium pressure of oxygen if the partial pressure of nitrogen dioxide is 0.4 and the partial pressure of nitric oxide is 0.27? Well, you plug the values in there. The partial pressure of oxygen is Kp. You're rearranging it. And see, this is the term you want. So you just rearrange these. This goes up at the top there, and that goes down the bottom. And this is what your new form is there. You put the values in there related to each. And you get 347 atmospheres. So basically the partial pressure of that is 347 atmospheres. Heterogeneous equilibrium applies to reactions in which the reactants and products are in different phases. And an example here is calcium carbonate goes to calcium oxide plus CO2. And you plug the values in there again. But you notice there's two solids and such like that. And the solids are essentially considered constant. So basically they don't change. So this is a constant and that's a constant. So they're not involved in it. You just get a new Kc. And notice the prime here, the new Kc is this because the CO2 is the only thing that changes. Okay, so the Kc prime with the concentration of calcium carbonate over calcium oxide. And since you have the same amount of moles of both, they'll essentially cancel out. And so the Kp will be the partial pressure of carbon dioxide under those conditions. The concentrations of solids and pure liquids are not included for the expression for the equilibrium constant because they're essentially considered to be canceling each other out when they're in there. Now let's look at an example here regarding each of these. You have calcium carbonate with a solid on the left and CaO mixed together. And then you've got more CO2 under these conditions. Now you have calcium carbonate there related to that, a different amount after the reactions take place. And this could be dependent on the temperature. So the temperature will kind of shift it in the right to the right, and we'll explain that, why that happens later. The partial pressure of the CO2 equals the Kp under those conditions. So notice into that, it's essentially going to be the same there. The partial pressure of the carbon dioxide does not depend on the amount of calcium carbonate or calcium oxide, because essentially those would essentially cancel out because you still have the same number of moles of calcium in both. Now consider the following equilibrium at 295. The partial pressure of each gas is 0.265. Calculate Kp and Kc for the reaction. Well, you plug the values in again. You set up the formula and you get the Kp is 0.702. Now what does this tell you? This is a small number. This is small. So which direction is the equilibrium going to be? Yes, it'll be to the left. So essentially, under those conditions, it will be to the left under those conditions. The Kp, Kc, you can rearrange that, the difference in the delta N for both. You have a change in the number of moles of 295. So basically you plug the values in there and you get 1.2 times 10 to the minus 4. And again, we already saw that where this is also very small. And so yes, it goes to the left. The equilibrium will go to the left. Now A plus B goes to C plus D, K prime C, and then C plus D goes to E plus F. That's a double prime C. And basically, it all depends on certain kinds of reactions that would continue reacting to form another form. And so basically you can get these relationships between both there, and essentially going all the way, A plus B goes to E plus F there. The KC there will be EF over AB there, and you can kind of see the relationship between both. KC is going to be KC prime times KC double prime. If a reaction can be expressed as a sum of two or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constants of the individual reactions. So that would be if you had a reaction that looked like this, where you start at this point, you go to intermediate, and then you go down there. Okay? And again, these are going to go in this direction. They'll also go back in the other. And it all depends on the temperature and other factors related to each. So that's the kind of thing where you could get two different reactions occurring in the same curve. Now let's look at an example here where you have N2O4 goes to 2NO2. Okay, the K prime there goes to, the K prime is the reverse of this. That's equal to 1 over K in this case. That's 216. So if this is the K and it's very small, what does that tell you? It'll tell you it goes to the left. And if this is the K that's very large, it tells you it's going to go to the right. When an equation for reversal reaction is written in the opposite one, the equilibrium constant becomes a reciprocal of the original equilibrium constant. Writing equilibrium expressions. Okay, the rules are these. The concentration of the reacting species are expressed in moles per liter. In the gaseous phase, it can be in moles per liter or in atmospheres. The concentration of pure solids, pure liquids, and solvents do not appear. The equilibrium constant is a dimensional quantity. In quoting the value for an equilibrium constant, you must specify the balanced equation and the temperature. So always write this first, and then that. If a reaction can be expressed as a sum of two or more reactions, the equilibrium constant is given by the product of the equilibrium constants of the individual reactions. So the next phase is, how does this fit? We end with chemical kinetics. Well, this is important too. For example, if you've got A plus 2B, you've got a forward K and a reverse K. The rate is going to be equal to this in this condition. You have the K forward, A times B squared. The rate reverse will be K reverse times the concentration of AB2. The equilibrium, the rate F equals the rate R. So under those conditions, you can have them be equal to each other at equilibrium. So if the rate F equals the rate R there, you can then equate these two equations and you get a new constant there. Kf divided by Kr is equal to Kc. And that is what we talked about originally. The reaction quotient is calculated by substituting initial concentrations and products into the equilibrium constant expression. If QC is greater than KC, it goes from the right to the left to reach equilibrium. So basically, if you got initial concentrations of the reactants and products into the equilibrium expression, and the QC is much greater than that, it'll go for the right reactants. Essentially, if KC is greater than QC, it'll go to the products. If QC is greater than KC, it'll go to the reactants. If it's at equilibrium, they'll be equal. And then QC less than there, essentially you'll have the reactants go to products there. So essentially you've got the two different relationships between both. So let me see if I can fix this slide here. And, we'll fix the slide just a second here. I'm going to share the screen again with you now. Okay, here we go. If QC is greater than KC, it proceeds from the right to the left to reach equilibrium. If QC equals there, so essentially you have the QC greater than KC, these are reactants to products. If you have it going the other way too, it'll do it the other way. Okay, back to share the screen again with you now. Maybe this will be a little bit more clear. If the QC is less than KC, the system proceeds from the left to the right to reach equilibrium. There, the reactants will go to products. If QC equals KC, the system's at equilibrium. And then if QC is greater than KC, the system proceeds from the right to the left to reach equilibrium. Calculating equilibrium concentrations. Okay, so let's continue to the next part and go back to the PowerPoint again. Share the screen. Calculating equilibrium concentrations, very, very important aspect of this. Express equilibrium concentrations of all species in terms of initial concentrations at a signal unknown, which represents the change in concentration. Write the equilibrium constant in terms of the equilibrium concentrations, knowing the value of the constant, solve for X. And then having solved for X, calculate the equilibrium concentrations for each species. So let's look at this next thing. At 1280 C, the equilibrium constant for Kc is 1.1 times 10 to the minus 3. What does that mean first? Does it go to the right or to the left? Yes, it's very small, so it'll go to the left. If the initial concentration is 0.63 for bromine and the bromide is 0.12 there, or just the regular, as the ionized one, Calculate the concentrations of these three species at equilibrium. Let X be the change in the concentration of BR2. Okay, so we set up a chart. This chart is very important here. You start with the concentration of the bromine at 0.063. The bromine atom itself is 0.012. That's the initial. The change there will be minus X. And notice you'll lose from this when you go to the right. This will become minus X. That's what it goes to the right. That'll be minus X. So you'll lose that amount of it. And this will become plus X. Okay, plus 2X because there's two of them. So you have two aspects to this. So it'll be 2X because you have two bromines. This breaks up and you get plus 2X for the change. The equilibrium there will then be 0.63 minus X. The other one be 0.012 plus 2X. And that's called the ICE method. So you now plug the values in there and see what you get with it. Solve for X. And the key thing here is when you solve for X, then you can make some assumptions based on you make assumptions based on the amount of material you're dealing with. And because X is relatively small, you can make some basic assumptions regarding both of them. So let's look at the equation again. Well, this is first, you kind of have those here. You multiply the top one out and then have that equals 0.0693 minus 0.01 like that. There, 0.011x. You just rearrange the equation. You put the things in a quadratic. ax squared plus bx plus c. You then use the quadratic equation to solve it. And you get x equals 0.0105. Both of those are the values of x. So you plug those values in there and see which one works. There's two possible values of x that could be a possible answer. At equilibrium, it's minus 0.09 molar. Now, is that possible? No. Okay. Or 0.0844 molar. Why is this not possible? Why is that not possible? Well, because it's a negative concentration. Doesn't work. So the other one will be 0.0084. So basically that X will be the one that will work correctly. So at equilibrium, you use 0.062 minus X equals 0.0648 there. And that gets you the value that you wanted for that. Now, Le Chatelier's principle is a very important concept for this. If an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset as the system reaches a new equilibrium position. Changes in concentration. For example, if you have calcium oxide plus CO2, going to calcium carbonate. If you add CO2 to this, it'll force it to go in that direction. That's a changing of the concentration to force it to go in a certain direction. Okay, so in this case, if you add this or this, that'll force it to go to the right. Or if you add this, that'll make it go to the left. Adding ammonia, it'll force it to the left to go to the stress. And this is a proof of experimental results. Adding ammonia to it, it changes the equilibrium. Change in concentration continued. You have essentially adding to the right-hand side will force it to go to the left. Increase the concentration of products shifts it to the left. You remove things from that. For example, if you have calcium carbonate goes to CaO plus CO2, and you remove CO2, that will cause the reaction to go to the right-hand side. Decrease the concentration of products, it shifts it to the right. If you add to the left, increasing the concentration of reactants, it'll push it to the right. If you remove reactants, it'll push it to the left. Decrease the concentration of reactants, that'll drag it to the left. Now, Le Chatelier's principle basically is summarized by that with changes in volume and pressure there. You have two gases. This would be based on the number of moles of each gas. So this would have 1 mole here and 1 mole there. So that would be 2 moles goes to 1 mole. Okay. So basically you increase the pressure. That's adding there. It'll shift it to the right where it has less moles there. So that'll shift it side with the fewest moles of gas. If you decrease the pressure, it'll go to the sides with the most moles of gas. You increase the volume, side with the most moles of gas. Decrease the volume, side with the fewest moles of gas. So it's all based on moles again. Very important. Changes in temperature. If you got an exothermic reaction, the K decreases. If it's endothermic, the K will increase. So if you've got an exothermic reaction that's like this, A plus B, and you got a situation like this, so you add pressure to that, you add temperature. Remember, this is the activation energy, and this is the activation energy to the right, activation to the right, and this will also be activation to the left. So basically you can get a variety of things related to both of those based on increasing the temperature there. Decrease the temperature with an exothermic reaction, the K will increase and the K will decrease with that because you're essentially removing heat from it. So for example, if you've got a system where you've got sulfur plus oxygen goes to SO2 plus heat. If you add heat to this, adding heat to this, add heat, it will force it to go the other way to break those up. That'll break those up. But if you remove the heat, it'll cause it to essentially go this way. So even that's an equilibrium between both of those. So essentially, it all depends on this. For example, if you got heat plus calcium carbonate, or we could say even sodium baking soda, this, you add heat plus that goes to the other one. And then you get the calcium oxide plus CO2 or sodium hydroxide plus CO2. Adding heat to the right things, and this is essentially an endothermic reaction. Adding heat to the right, adding temperature will cause it to go to the right there. So basically, that's how that works regarding Le Chatelier's principle. So in this case, you've got the breaking up of the dinitrogen tetroxide. Is that an endothermic or exothermic reaction? Well, within those conditions, it's endothermic. If you remove heat from it, get it colder, it'll change back to the other one. If you make it hotter, it'll go to the right. So adding heat to it will cause it to go the other way. Now, adding the catalyst does not change decay. And again, the reason for that is, if you remember what the curve is, what a catalyst does, if you've got an activation energy like this, the catalyst makes a different pathway for it. This is with a catalyst. And basically what it means is the reactions will go back and forth easier going the other way with the catalyst. It essentially does not shift the position of the equilibrium there because it reacts, essentially, it speeds up reactions in both directions. Speed up reactions in both directions. So they essentially cancel out. The system will reach equilibrium sooner. And in some cases, that is important. So if you have those reaction in progress, potential energy there, and then there you have essentially the catalyst lowers the EA for both the forward and the reverse one. So in this case, the forward is there, the reverse is higher. This one, it's lowered there, and it goes back the other way. So basically, the forward and the reverse goes the other way there. It does not change the equilibrium constant or shift the equilibrium. It just makes the activation energy for both be the same. Now, if we look at hemoglobin, high altitudes and hemoglobin production, okay, so for example, at high altitudes, if there's less oxygen at high altitudes, essentially what is that going to do? Well, you need more of the hemoglobin there, adding that to force it to go that way to enable the blood to carry more oxygen. And that's why people, after a while, get more hemoglobin in the blood if they live at higher elevations. The Haber process is another example. The delta H is a negative value there, has to be compressed, catalyst there, ammonia condenser, it's removed from that. You take away the liquid ammonia, and essentially what you're doing is you're removing the ammonia from it, and that drags it in that direction. So essentially you remove that from it, and this gets shifted back into it to go through reaction again, and that's the Haber process. Le Chatelier's principle basically says with the concentration, it shifts the equilibrium constant does not change. With pressure, it shifts equilibrium, depends on the relative moles of that, no equilibrium constant. The volume shifts equilibrium, depending again on the moles. The temperature, yes, it'll shift equilibrium. and it changes the equilibrium constant, because essentially you're getting the activation energies reach in both directions easier or less easy. So the catalyst does not shake the equilibrium. And also another reason here is you get more collisions. We are done. So I hope you enjoyed the lecture, and thank you very much.